Start the recording? Yeah, it did. Okay. So today we are starting the analysis lecture series. Specifically, we're going to be focusing on, I guess, like single variable real analysis. Although once you have the tools of topology, which I covered in the last lecture series, multi-dimensional real analysis isn't that much harder. And from there, you could branch off into, say, the like the manifold lecture series that I did, or you could go to complex analysis. But those won't be things that we'll be covering. We're just doing the fundamentals of real analysis because you get really like the main things that you need to know for the other fields. So without further ado, in this first lecture, we're going to be constructing the real numbers. Now, there are a lot of different ways to do this, but the nice thing is that the real numbers, as they're defined, they all represent the same thing. They're all essentially unique up to what we would call an isomorphism. So what we are going to do is build up the definition in several parts. First, the real numbers are a field. So we need to define a field. Now, a field is a purely algebraic structure, and we're going to talk more about field theory in the algebra series. But we need to define it here for the real numbers. And we don't really need much of field theory, we just need the definition of a field. So a field is a set F with two binary operations, which we denote as plus and times. So we just call these addition and multiplication. And what a binary operation means is that these are functions from f times f, so the Cartesian product of f with f, and it maps into f. So these are just functions, right? And instead of writing this as like a function, like plus of a and b, we just write a plus b, right? We just write it as we have, as we normally would, right? And for multiplication, I'm usually going to be holding the dot, and so instead of a dot b, I'll just write ab when it's clear. Now this isn't all there is to the definition of a field. The first thing is that, and it's sort of written explicitly, or I guess implicitly in this, what I've written here, but that is closure, and that is that a plus b and a times b have to be elements of f, right? So I'm going to say a, b, and c are all going to be elements of f. So if I take two elements of f and I add them or I multiply them, then I have to get another element of f. The next property is going to be commutativity, which is that the order in which I multiply or add does not matter, right? The third property is associativity, which says that if I have three elements, then the order in which I operate on these three elements doesn't matter either. If I add b and c first and then add that to a, it's the same thing as adding a and b first and then adding that to c. And similarly, we have associativity of multiplication. And so these are things that we're sort of used to in like all the math we've done up to this point, right? Or at least, like calculus, like real numbers, rational numbers, whatever. We're used to these things being true, but there are important algebraic structures which don't satisfy these properties. So it's important to specify that we do have these properties here. The next property relates multiplication and addition, and it says that a times b plus c is equal to ab plus ac. The next property is that of identity, which is that we have two elements 0 and 1 in F, such that 0 plus a equals a, and 1 times a, and here I'll write the dot just to be clear, 1 times a equals a. And we further assume that 0 is not equal to 1. The sixth and final property for a field is that we have inverses. In particular, we have a negative a, or we denote it as negative a in F, which just means that a plus negative a equals 0. And if a is not equal to the 0 element, then we have an inverse of a, which means that a times a inverse is equal to 1. You can also prove that inverses are unique. One thing you can also show from this 0 is that 0 times a equals 0. And there are a couple ways you can do this. You can do there's a way to do it explicitly. There's also a way to do it by contradiction, like assuming this side is not, well, actually, I guess that wouldn't work because you'd have to take care of the case of 0 times 0. So I guess that wouldn't really be worth anything. But you can do this explicitly, and it's something you should do just to practice using these field axioms. So for an example of a field, we can consider the smallest field, which just consists of 0 and 1, with the added restraint that 1 plus 1 equals 0, and otherwise all the addition and multiplication rules are the same as we would expect, but we have to specify that 1 plus 1 equals 0. Then this is a field, and it's denoted as, actually I'd rather denote it like this, z mod 2z, right? So this is the field which you essentially get by considering classes of even or odd integers. You can treat that as field elements. So that's the field axioms, but that's not all we need for R, because there's bountiful examples of fields, right? We need more properties to nail down what we want as our real numbers. The next thing that we want is a set of order axioms, right? So an order is going to be sort of a relation on A, so that we can take, or not A, but our the set that we're constructing, so that we can take two elements and say whether A is less than B, right? So these axioms are as follows. We have transitivity, which says that if A is less than B and B is less than C, then A is less than C, right? The next axiom is preservation of order. If A is less than B, then A plus C is less than B plus C. And if C is greater than 0, then AC is less than BC. Otherwise, or not otherwise, but if C is less than 0, then you would reverse the order. Right? And that's something we're familiar with, but you should also prove that. And the proof of this is essentially saying that negative C is greater than 0, and then using negative C in conjunction with this order axiom. The next thing is called trichotomy, which says that exactly 1 is true for any A and B that you pick. Either A is less than B, B is less than A, or A equals B. So if I take any two elements, they have to satisfy one of these properties and only one of these properties. So now we have introduced an order on our field. But this is not all that we need, right? There's still this next property, which is the Archimedean property. This says if x is greater than 0, there is an integer n, or a natural number I should specify. And by the way, we haven't formally introduced the natural numbers. There are two ways to do this. One is through the so-called piano axioms, which you can look up, and it's sort of just an axiomatic way to construct the natural numbers in the same way that we're using these axioms to construct the real numbers. Another way to do this is to just define these natural numbers from our field by saying that it is the smallest subset of our field containing 1, and it's closed under addition. So in other words, it just consists of 1, 1 plus 1, 1 plus 1 plus 1, and so on. So back to our Archimedean property. If x is greater than 0, then there is a natural number n such that n is greater than x. And so essentially what this is saying is that if we use this definition of the natural numbers, it's essentially saying that we can add our multiplication identity 1 over and over and over again, and eventually we will get something bigger than x. Right? And so now we have what's called an Archimedean ordered field, which I'll just abbreviate as AOF, right? Archimedean ordered field. But this, even though we now have 10 properties, this is not enough to pin down the real numbers. As an example, we have the rational numbers, which consists of fractions a over b, where a and b are integers. And again, you can sort of define the integers from the natural numbers, and therefore you can define the rational numbers. This is an Archimedean ordered field. But this is not the real numbers that we're looking for. And the reason that there's a problem with this is that equations like x squared equals 2 are not solvable in the rational numbers, i.e., there is no square root of 2 in the rational numbers. Now, it isn't all about being able to solve equations, because even in real numbers, right, Like, for instance, you can't solve x squared equals -1, not solvable in R, right? For that, you would need the complex numbers, which is the algebraic closure of the real numbers. But rather, the idea of extending Q to R is the idea that that we want certain sequences to be convergent. So now we're going to talk about that. First, I want to mention something that I mentioned in the last video from topology in metric spaces. I mentioned that in real numbers, and technically this exists for any ordered set, or at least an ordered field, I guess, because you need 0. There is an absolute value function, which if a is greater than or equal to 0, then we return a, and if a is less than 0, we return negative a. Now, you should prove that for any two a and b, the absolute value is less than the absolute value of a plus the absolute value of b. The proof of this, as I mentioned in the metric spaces video, uses cases on a plus b. And the two cases are if a plus b is greater than or equal to 0, and a plus b is less than 0. So that should be a hint, but you should go through the proof for yourself. And so this is the triangle inequality, which in turn tells us that R is a metric space with the absolute value of x minus y as our distance, or our metric function. And this isn't exclusive to R, I guess. Technically, you could have this on Q, right, the rational numbers. But this is sort of going to help us later when we talk about the topology of R. The final condition that is going to separate the real numbers from the rationals is called the completeness axiom. This states that every Cauchy sequence has a limit. So we will talk about what this definition means, right? We'll define what a Cauchy sequence is in the next video. But this is the key defining property for R, at least in terms of separating it from the rational numbers. The rational numbers do not satisfy completeness. In other words, you can construct this thing, which is called a Cauchy sequence, which does not converge in the rational numbers. An example of that, the rational approximations (1, 1.4, 1.41, 1.414, etc., of square root of 2 are, this is a Cauchy sequence, yet do not converge in Q. So this completeness is what's going to set apart the real numbers and the rational numbers. And as I said before, it is possible to prove that any two complete AOFs, so Archimedean ordered fields, are isomorphic. So R, as we've constructed it, is unique. Or we would say it's unique up to isomorphism. And so that's it for this lecture. Do you have any questions?
Okay, okay.
All right, that's it.